So, like Rob said, I will be talking about the X-ray universe, the satellites that we use to observe it, and the science that we are exploring right now. So, I'll give you a general overview of X-ray satellites, but I'm also going to give you a really unique perspective, behind the scenes look, if you will, on what it takes to build a satellite. So I did my PhD research at Cannonball University, where I was part of a small group that designed, constructed, and calibrated 2 X-ray optics that are in the NuSTAR satellite that's pictured above. So you'll get all the nitty-gritty, dirty details of what it takes to build something to go into space. Okay, so before we get into X-ray astronomy specifically, let's talk about the general electromagnetic spectrum. This is just a collection of different types of waves of light, ranging from very low energy radio waves all the way on one side, and high energy gamma rays all the way on the other. So smack in the middle, we have visible light, the light that you and I can see with our eyes. And that's denoted by the color rainbow bars in the middle of the spectrum. So if you look at something with your eyes, you get very specific types of information. You get color and shapes, basically everything that you and I can see. And this helps us distinguish faces, talk to people, avoid obstacles on the street. There's a lot of really useful stuff that we get just by looking at something. But if you look at the EM spectrum in general, you can see that the visible part of it makes up only a tiny, tiny fraction. So there's all kinds of light that we just can't see with our eyes that also carry very similar information to what we see when we look at a chair. So the top bar, the black and white Y and N, denotes whether or not these types of EM emission, or light, penetrate the Earth's atmosphere. So why is this at all important? Well, if we're looking at something in the sky, we need to know whether or not that light from that particular object, or star, or supernova, will come reach us down here on Earth. So something like radio waves, for example, penetrate the Earth's atmosphere really, really nicely. And so we can build large, for example, 64 meters of the Park telescope, large telescopes right here. This lets us build them very big. They're heavy, they're the size of buildings, and they're really sturdy. And we can get a lot of really cool information from them. CHIME is just another example of a ground-based radio telescope. There are several professors here at the university that are heavily involved in helping build CHIME. So if we go towards the middle of the spectrum, back to the visible light, you can see that visible light does come through our atmosphere. But the atmosphere has clouds, it has wind, it has all these slight perturbations that can kind of blur or fuzz out an image. So we do have ground-based visible light telescopes, but, for example, we have the Hubble, which is a satellite in space, and it takes amazing pictures of visible light that comes from a whole bunch of different types of astrophysical objects in the sky. So if you look all the way towards the other side, towards the gamma rays, you can see that these rays do not penetrate the Earth's atmosphere. So we have to develop gamma ray telescopes like Integral to float above the atmosphere and take pictures of things that do not come through the Earth's atmosphere. X-rays are towards the higher energy side of the EM spectrum, and you can clearly see that these also do not come through our atmosphere on ground. So if we want to look at something using X-ray light, we have to put a satellite in space. So all of the majority of the X-ray telescopes that we're using now, they're all in orbit around the Earth. So why do we even bother looking at X-rays at all? So if you take a look at something simple like your hand, right? You can see with your eyes information that the all of a sudden you get a completely different set of images. So you can see, for example, little tiny bones. What looks like a solid piece with your eyes is clearly composed of tiny sections put together. You can see whether or not a bone is broken, you can see how many there are. And so this gives you a totally different sense of something just as simple as your hand. So we do something very similar when we look at sources in our universe. So this is a picture of the Crab Nebula. It's a supernova remnant. And these are pictures taken at various wavelengths of light. So it's radio and IR and the visible from the Hubble telescope all the way up to the high energy gamma rays. So a conceptual idea of a supernova remnant is a snapshot of an explosion. So the star has gotten very old and died, and it's exploding out into space. And what we're seeing is a picture in time of the explosion as it propagates outwards into space. And that's a very clear picture taken in the radio, IR, visible, and UV. It looks like some amorphous blob-like structure that has some filamentary structures in it, and it looks really pretty. But it looks like a round, oblong potato. And there is tons of information that we can get from this oblong potato. There's science that is done just in the radio and IR visible light that gives us amazing pieces of information about the supernova remnant itself. But if you take a look at the X-ray, which is the blue structure, the blue picture on the middle of the bottom, it looks totally different. So what looks like a blob in other energy bands looks like a disk that's maybe spinning, and two jets that are coming out, and some kind of swirly structure. It looks totally different. So if you put two images together, for example, this is the visible from Hubble and the X-ray in the light blue in the middle, what you're seeing is the supernova shell on the outside, and on the inside, the X-rays look through that supernova shell, just very similar to the way your X-rays look through the skin of your hand, and we can see that there's something going on inside. So there's a pulsar or neutron star, a very tiny packed rock, that's spinning really, really quickly, and it's whipping around particles that get caught up in the magnetic field, and that's what's causing the disk-like structure in the middle and the two jets that are coming out outside. So even something like putting together just two energy bands together gives you a much better understanding of what's going on in this complex object. So I'm also going to use the term sources, and I want to make sure that we're all on the same page. When I say source, that means any object in the sky that emits X-ray radiation. So that can be anything from black holes to white dwarfs to neutron stars. The supernova remnant is a very good example. At the bottom is a wonderful NuSTAR image of Cascade, which is a very well-known supernova remnant. So some of these objects, or sources, are very close, and we can see that they have a shape. There's some structure to them. The supernova remnant looks like a big potato, for example. The galaxy on that end looks like a spiral galaxy that you've seen pictures of. But some objects, like the black hole example, which is the two pink dots you see in the IC432 image, that side. So those two black holes, which are pink, are very small, and they're also very far away. So they just look like tiny little dots. So some of the items we're looking at are round, and they have a structure, and some are very small or far away, and they look like tiny dots. The other thing that all of these objects have in common is that they're really violent and energetic. They're moving really quickly, or they're slamming into each other. So a supernova remnant is a violent explosion, that material out. And so these are very high energy, exciting things to look at least I think so. So if we wanted to look at something in space, we usually build a telescope to help us look and zoom into these pictures that are unavailable to us just by looking at them. Normal telescopes that work in, for example, the radio or the visible light, they either refract light using a lens, like the top left image, or they reflect light by bouncing it directly off of some kind of mirror or a specific coating on a piece of metal. But if we took any of these telescopes that you see up here and tried to look at X-rays with them, X-rays will just go right through. You'll see nothing, and all of that time will be wasted. So we have to come up with a completely new way of looking at X-rays because all of the other options that we have just simply won't work. And so the Volter Type 1 X-ray optic is exactly what we need. So there's a lot of stuff on that page, and it can be really confusing. But a simple way to think of it is imagine yourself on the edge of a very calm, quiet lake, and the water is nice and glassy in front of you. Think of the water as your mirror, and then in your hand you have a small rock. That rock represents an X-ray coming out of a supernova remnant, for example. So if you take that rock and drop it into the water, it's just going to go look right through the bottom. And that's exactly what happens with the other telescopes. But if you take that rock and you skip it across the water, it will bounce very nicely and just kind of keep going. And that's the idea. So there are some really great things about a Volter Type 1 optic. For example, it has high sensitivity and low background. And that's exactly what you want out of a really good camera. But there are sort of problems. It makes it very difficult to build. So one of the issues is that you have to have a lot of these little mirrors kind of stacked very close to each other so that you can bounce a whole bunch of these X-rays. And that means there's a lot of very thin or delicate pieces put together, and it makes it very difficult to build. The other hard part about these optics is that you have to have the detector or your camera very far away, because you're bending the light only a tiny, tiny bit, and it takes a while for all those rays of light to come together onto a single point. So the long focal length makes these telescopes really, really long. So let me take a little bit of a detour and talk to you about the actual telescopes that we have operating right now. So on the graph above me is a scale from 0 to 120 that's going to map the energy in keV. So you don't really need to know what keV is, but you can get it's a measure of the amount of energy that a single X-ray beam contains. And if you ever go to the dentist and get a picture taken of your tooth, that X-ray that they're using is about 20 keV, so sort of on the lower end of the spectrum, just to give you a sense. So if we start with one telescope, we're going to start with Chandra. Chandra has a number of cameras on it that look at X-rays. ASIS is one of them. And Chandra is a state-of-the-art X-ray telescope. It was launched, I think, in 1999, if I'm correct. It has really great X-ray capabilities. And that little schmutz that you see under ASIS is not a smudge on my screen. That's a representation of the blur of Chandra. So just like you take a picture with your digital camera, it looks really nice and crisp, and then you zoom in, zoom in, zoom in, and then what looked like a very clean line is now this fuzzy barrier. So every camera has a blur or a resolution inherent in it, and Chandra's is represented by that So another X-ray telescope that's orbiting is Newton. It has a number of different cameras on it. This one specifically is the Epic P10 camera, and it operates from 0.15 keV to 15 keV. Chandra ends at 10 keV. So by using XMM, we gain 5 whole keV. That may not seem like a lot, but that's a lot. The problem, or one of the downsides, I should say, of XMM Newton is that the resolution of the blur is just a little bit worse than Chandra, and that's represented by the slightly bigger white dot. The third low-energy X-ray camera is the Swift XRT camera that operates from 0.2 to 10 keV, and its resolution is represented by the even larger white dot. So these guys are all sort of towards one end of the spectrum. On the other end, we have Integral, which has a camera called Nevis on its telescope, and it operates from 15 all the way up to 1,000 keV. That's like way off the scale. So Integral lets us look at the really high energy stuff, which is really cool. But it has a problem. If I put up a picture of the blur of Integral, it would look cute. So Integral is really, really useful. We're just going to push that all the way to the side. Integral is really useful when you want to look at really bright, energetic X-ray emission from objects. But it's not really great at telling apart if you have two guys very close together or if it's just one big thing. So what a lot of astronomers do is they take a picture of the same object with two different telescopes and you get a sense of how things look across all resolutions and all energies. Now, NuSTAR, which is the telescope I worked on, was meant to be a bridge between the stuff on this end and the stuff on this end. So it runs from 3 to 80 keV, so it overlaps both telescope ranges, and its resolution or blur is represented by that. And it may seem like this is going to be a really blurry picture, but it does enough to give us some amazing snapshots of what our galaxy looks like and what our universe looks like. So there's one more piece that not a lot of people talk about, and that is the cost of all these telescopes. So Chandra cost $1.85 billion to construct and launch. XMM Newton came in a little bit under at $730 million to build and launch. And NuSTAR comes in at $160 million for the construction, the launch, and the operating costs for its lifetime. So it was specifically designed to be a low-cost X-ray satellite. And I want to say that Chandra and XMM are worth every penny. They are awesome telescopes. So it's just by design that NuSTAR was slated to be a low-cost telescope. So what is NuSTAR? I keep mentioning this magic word. So NuSTAR stands for the Nuclear Spectroscopic Telescope Array. The spectroscopic part implies that it looks at energy and images of different things. And it's an array because there are two optics and two detectors. Kind of like your left eye and your right brain work together, and your right eye and your left brain work together. So NuSTAR has one pair optic detector, and then right next to it, another optic detector. So the detectors are on that side. So the detectors are on that side. They were manufactured at Caltech and JPL. And the mast that separates the two in the middle was made by a company called ATK that has previously been used for instrumentation on the International Space Station, or ISS. And then the two optics were developed at Columbia with help from DTU Space in Denmark and NASA Goddard in Maryland. So I'm going to go through the optics construction. That's the process I was heavily involved in. And I'm sort of skipping a whole year and a half of research and development to make sure we had the right material, the right procedure. We had made sure that everything we put together would survive not only launch, but the harsh conditions of space. And so there was a lot of putting together little test samples and ripping them apart, and putting them together, and then ripping them apart. So I'm going to skip the R&D part, but you're welcome to talk to me later if you have any questions about how glue dries. So once we had everything put together and ready to go, we started with the construction. So on the inside is something about this width, about twice as long, that we're calling the inner mantle. It was made from titanium. It had two main purposes. The one main purpose was to hold all of the stuff that we built on it, which you'll see in a moment. And it had connectors on either end that connected the optic to the rest of the telescope. So we first put down strips of epoxy or glue. We put them down from one end to the other in a very thin, precise line. And then the equipment that held the manual during construction, which was part of a very sophisticated CNC machine or a computer numerical control machine, and it would rotate a little bit, and we put another line down, and then we rotate and put another line of epoxy down. And then on top of each strip of epoxy, we put graphite, what we're calling spacers. And somewhere I have a pencil. So you can think of the graphite spacers as exactly what's inside your pencil. It's a very similar material, it's a very similar shape. Ours is square, this is round. But the overall idea is that you're putting these thin little wires of graphite on top of these thin little lines of glue. And the machine then would rotate, and we would curve those square corners of the graphite into precisely the exact position that we wanted our glass shells to be. And then another layer of epoxy, and then the glass shell on top. This, by the way, is 1 day's worth of work. We had to put everything down, clamp it down, let it sit overnight, take apart the clamps, and do the whole thing over again the next day. And so we would end up with something that looked like stacks of spacers or graphite on top of each other, and the glass layered one on top of each other. Sort of like soda cans, if you cut the top off and just stacked one inside the other, like an onion type. That's exactly what this looks like. And so this is an edge-on view of the actual optic. So you can see the vertical rows of the stacks of the graphite, the thin lines that look like lines on a record player, I still remember what that is. Those are the edges of the glass pieces that we're using. They're very thin, they're 0.2 millimeters. That's almost the thickness of a piece of paper. So you can better believe you drop a whole bunch of these glass pieces that shatter. And this is what the optic looks like at its midpoint. And as we start layering these very tiny, thin shells, it gets bigger and bigger and bigger. And this is what the final product looks like. So on that side is the final epoxy optic, and you can see the reflection of my friend Todd. He's wearing a bunny suit. This is all built in a very precise Class 1000 clean room that was temperature controlled, humidity controlled, most importantly, dust controlled. So every day that we would go into this, we would have to put on pants and the booties and the hat and the mask and the gloves. And it would be quite warm in there, so everybody got really stinky and sweaty. But it was exactly what you'd imagine a high-level telescope built to be. Very clean and precise. It had a lot of controls for what we could bring in and what we could bring out. So bringing a camera in here was actually somewhat difficult because you have to clean everything that went into this clean room. And so I don't have a lot of pictures of the build process itself. Over on the right, you'll see the final optic, and it is enclosed in what we call spiders, the two end caps that are attached to the manual, and the ring around the inside is a support ring that will hold the thermal blanket that goes over the optic. So we built a whole bunch of these things. We built one 30-layer test optic, one full-size test optic, and two full-size real optics that we called A and B. We're really creative. Each optic was about 47 centimeters long. It weighed 31 kilograms. The titanium manual did not weigh a lot. Your graphite inside your pencil does not weigh a lot. So about half of that, or more than half of that, was the glass and the glue. Each optic had 133 layers. So if you think of a layer per day with a couple of vacation days built in, each one took about 8 months to build. So that's a lot of time. And we built 2 of them simultaneously, but still, that's a lot of time. We finished the A module in August and the B module in September of 2010. So just for reference, that big thing is the Chandra optic alone. And that tiny little thing is the NuSTAR test optic. And so they're hugely different in size. So once we built these optics, we have to calibrate them. And that is very similar to figuring out what the prescription of a pair of eyeglasses is that someone just handed you off the street. So if you took these random eyeglasses and you put them on your face, you can quickly tell if they make your world fuzzier or blurrier. You have just calibrated those eyeglasses. But we can't do that with these 31 kilogram optics. And you can't put them up to your face and shine x-rays because, well, you just won't survive the test. So we had to come up with a totally different way to figure out what this prescription is. And we chose to do this at Nevis Laboratories, which is a very historic, old facility that Columbia University runs on the outside of New York City. Back in the 40s all the way to the 80s, there was a functioning cyclotron in one of the large buildings that was used for the Manhattan Project. The head of Nevis Laboratories, James Rainwater, won a Nobel Prize for his work that he did in this building in 1975 for smashing together atoms and figuring out what's on the inside of an atom. So there are 2 main parts to this building. One is the giant cyclotron itself, which is a huge, hard, truck-sized magnet that spins particles really, really quickly in a circle. And the other part is the tunnel that you see on the other end. And this tunnel is 525 feet long underground to prevent people from walking through beams of particles everywhere. And it was designed to be that long. There's a structure that runs from one end to the other that helps the particles move quickly from one side to the other, where they would then collide with other particles and then detected. So these pictures are from 1940 and 1962, and nobody works in suits and ties anymore. I think it's super quaint that people would come in and work in a dirty physics laboratory in a suit and tie and bowler hat. We just use t-shirt and jeans now. So we thought we were inheriting this wonderful old building, and granted it was decommissioned in the 80s, so it no longer functions as a cyclotron, but it's still used for science and other purposes. And we were really excited to come in and take over this old location, and instead of that, we inherited this. And that, and that. So all this stuff has been sitting and decaying inside a very damp, very cold, very long tunnel. So to balance out the year I spent in a clean room, I spent 2 months cleaning scrap metal. 2 very different ends of the spectrum. So we put together the Rainwater Memorial Calibration Facility. So I'll walk you through the different components here. On one side, you have the source, which is a tiny little X-ray beam, kind of like a laser. It runs through this very long set of pipes that we vacuum down. So remember I said X-rays have a hard time going through our atmosphere. They have a hard time going through air. So we want to have this as vacuum down as possible to make it easy to go from one side to the other. Then there's a yellow bar that indicates the big concrete wall between the tunnel and the big building that holds the old cyclotron. And there we built a room for the optics, which is again a clean room to make sure the optics stays pristine. Another set of pipes that mimic the distance between the optic and detector on NuSTAR, and then the detector room itself. So end to end, it was about 173 meters. So what you can think is everything on this side of the yellow wall is your astronomy object with your long distance of space in between, and everything on this side is NuSTAR. So let's start with the pipes. Now, if you're working with vacuum pipes, it's almost the standard material of choice to use stainless steel. But if we have 525 feet of stainless steel pipes, that would be really, really expensive. So instead, we use PVC sewer pipe. And the running joke in our group was that I was chosen to be one of the few people that worked on constructing this calibration facility because I could fit into the smaller pipes that can be used. And it's a sort of joke, but totally true. So it was not glamorous work, but it was really exciting, and I worked with an amazing group of people to build this. So this is the tunnel with the pipe all the way at the source end. The pipe is really small because the laser dot from the X-rays is very small. And as it runs down the length of the tunnel, the pipe gets bigger and bigger. And then this is the end that comes out through the wall that you see right in front of you. And that's my friend Jason in the red shirt. He's 6 foot something. And to give you a sense, those PVC pipes came up to my hip. And we had to cross them every time we turned the lights on in the tunnel. Not fun. So this is the final image. It's nice and clean. It functions really well. And it was precisely aligned from one side to the other. So on the other side, we put the optics room, which again I mentioned was a very small, clean room. And we built a wooden structure around it to hold up lead shielding so that we could walk around and not be zapped by X-rays every day. And this is a final image of what the NuSTAR side of things look like. We had on one side the optics room, the tunnel, the piping that represents the mast, and then the detector room off to that side of the picture. And to give you a sense of scale, the pipe that runs from the optics room to the detector room was about my height, which I know isn't very tall, but it felt tall for me. So this is just a quick picture of the test optic inside the clean room. You can see the spider structure, and we placed it right in between the tunnel pipe and the mast pipe. And we could rotate this optic, shift it, and angle it, and take the prescription of every single piece on this optic. And after about 7 months of hard work and putting things together and cleaning things out, on January 14th, 2010, we turned everything on and it worked. It was awesome. So this is me and my 4 colleagues that were there turning it on, and the bottom image is the image that we got as it passed through the tunnel, through our optic, through yet another pipe, and onto the detector. And it's a small pinprick of light, exactly what we wanted to see. Now, in case that picture doesn't convey our excitement, we were really excited. We were also really tired. It's like 11 o'clock at night. We just really wanted to go home. So there is also a whole bunch of other stuff that went on behind the scenes that you can totally ask me about later. A lot of it is very precision-oriented or engineering, and a lot of it is cleaning out scrap metal. So I can go through all these in detail later. So once we have this optic, we have to figure out how to put it into space. And in order to do that, we had to give all of the components to NASA, who put them together for us, since we have no idea what we're doing there. So before we even started, I was such a naive student. I had no idea that things could go wrong. These are just 4 examples of things that did go wrong. Astro-E exploded during launch. It started to spew out rocket fuel from the side, and it started to go into a corkscrew, and all of this landed in the Pacific Ocean. The round 2 of Astro-E, titled Suzaku, was launched by the same company, and the lead instrument failed 15 days into launch. SpaceX, the Falcon 9 rocket, exploded on the launch pad during the test fire in 2016, not long ago. And Hitomi Astro H launched but lost communication. There was a misfire from a smaller orientation rocket, and it separated into 5 pieces. So each one of these failures represents about 3, 4, 20 of me that were relying on this telescope for the degree and for the rest of their scientific career. So if something went wrong with NuSTAR, I had no idea how bad it could be. But nothing went wrong. So for a full year, NASA took our telescope pieces, put them together, and put them into the rocket. So you can see there is the entire NuSTAR system compressed, ready to go. It's about the size of a refrigerator. And this is totally different from the really, really big stuff that I showed you that we were building at Nevis. And that's because the compressible mass lets us squish everything together like a slinky so that it was a tiny, small thing that we could send it into space. And the image on the bottom is NuSTAR being integrated into the rocket payload. So we launched NuSTAR from the Kwajalein Air Force Base in June 2012. Now this is a rocket that is strapped to the belly of a plane. The plane takes off, drops the rocket ignites, and then goes up into space. It's a lower cost alternative from the standard rocket launches that you see on a launch pad, but it's very violent. You can think of it as smacking a baseball that changes direction really quickly. And so the tiny, delicate, beautifully constructed X-ray optics that I worked on had to go through that. And I was the quality control officer, so if something went wrong, that was my butt on the line. So, this is the camera that was behind the rocket on the bottom of the airplane. And this is the last view that anybody had of visual contact with NuSTAR.
T-minus 15 seconds. Potters go for launch. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, drop. And Pegasus is away. Standing by for ignition. And we have stage 1 ignition.
It was such an exciting thing to see, to watch this thing get launched. So a little bit later, right after launch, about a couple weeks later, the mast deployed. So this is the slinky that expanded, that moved apart the detector and the optics. And this is an artist's visualization, so this is not a real picture, this is just some animation of what this looked like when it expanded. So this specific type of mast was used for a small camera at the ISS a couple of years ago, but it had never been used before on such large and heavy objects in space, nor has it ever extended this long. And when they first did a full test run of this, someone forgot to account for gravity on Earth. And one little cable got caught up in one of the stanchions, and the whole thing just mangled itself. And so production shut down for a couple days before they figured out what the problem was. So thankfully, this went off without a hitch. It took 9 minutes from start to finish to expand, and everybody called it the 9 minutes of terror, because we had no way of controlling or fixing this if something went wrong. However, a little bit later, in June 8th, we turned on everything and checked it out, and it worked. This was so exciting. So we looked at a very small object called SIG-X1, and remember I showed you integral looks at the high energy side of things? This top image is what integral saw when it looked at it, and the bottom image is what NuSTAR saw when it looked at it. So you can see the resolution is so much better. So now that this is finally up, we can do science. This is the part that I was waiting for so long. I loved constructing NuSTAR. I had an amazing experience there, but this is the bread and butter. So as a PhD student, I was involved heavily in calibrating in flight the optic, which is very similar to what we did on the ground, but we're now able to mimic that process but do it in space. And you always have some things shift around when you go through such a violent process. So we spent a little bit of time figuring out how all the components worked, and then we started to publish paper after paper after paper. So one of these papers that I started to look at is something called the Cannonball. So this is the center of our galaxy. This is our home. On the big orange picture over there is a radio image of our galaxy, of the center of our galaxy. And the black hole that powers everything around us is marked by a little black hash mark. Now, at some point in our galaxy's history, there was a supernova that exploded in the middle of the galaxy. And that potato, if you will, is what we have outlined here. It's called Sagittarius East, or Sagittarius A East. So, if you look at that tiny little arrow, the inset is a very small object that people have been looking at called the Cannonball. And it's moving. It's moving at 500 kilometers per second. But when you look at something this huge, it just goes from here to here in about 20 years. So we know that this object was moving, and we could look at it from various different wavelengths. This was just a radio image, but Chandra, the very great X-ray telescope, has also looked at this, along with a whole list of other telescopes. But nobody was able to really pin down what this thing is. So it could be something very hot, like a cataclysmic variable, or it could be something that's powering electrons, like a neutron star. We kind of had no idea. In many ways, it's like standing on the surface of the Earth, and you can see what's around you, very small little area, and if you zoom out and get all the energies together, you can see that the Earth is round. And so we wanted to use NuSTAR to get a better picture of what this thing was. So the blue, red, and white image is the same Sagittarius East picture taken by NuSTAR. So there's a lot of dots and dashes, but what's really important is the Cannonball comes up super bright, and you can see that in the image on the inside. So we took a look at this Cannonball, and we kind of, in using NuSTAR plus Chandra, which is the black line from NuSTAR and the red line from Chandra, we put these pieces of information together, and we figured out that this thing is almost certain to be a neutron star. So why is this at all important? Well, if you track how fast this Cannonball is moving, and you basically rewind the clock, if it started out at the green hash there, the center of Sagittarius East, and you take it at the speed it's traveling, it would end up exactly where it is now. So what we can kind of assume is that this is most likely the neutron star that's left over from the explosion that caused Sagittarius East. And this explosion kicked this tiny little rock so quickly that it's escaping its own supernova remnant, kind of like a bullet blasting through a piece of paper. So this was super exciting. And using NuSTAR, we were able to do things like measure the magnetic field of this neutron star. We measured the magnetic field of the pulsar wind around it. We got all kinds of really cool information just from this tiny little dot in space. So we also took a look at this same object, our center of our universe, and we started to look at things at higher energies. Now remember, the small focusing telescopes kind of stop at 15 keV, but NuSTAR can keep going to 40. So we took a look at the 20 keV emission from our own galaxy, and we found this weird haze everywhere. And the haze is contained inside that big green circle. And this was totally unexpected. It was not predicted at all So this was a brand new NuSTAR discovery. So what we used both the spectra, the type of light that's coming out, and the image that we took with the detector, and there were a couple of different options that we looked at to see what could cause this X-ray haze. And it was so useful and so new that this was published in Nature in 2015 by my colleague Tristan Perez. So the gist of what came before, you can kind of think of Sagittarius star and the stuff that's in our galactic center is a big old mess. There's a bunch of stuff going on. But if you look a little bit away, you can see individual things hanging out by themselves. And the pulsar ring nebula G21.5 is one of them. So we took a look with Chandra, which is the image over there. And it does a very good job of focusing X-rays very well. So we can see the pulsar ring nebula as an inner bright dot. That's the object that most people look at and analyze because it's very bright and contains a lot of information. But there's also this weird, hazy stuff in a circle hanging out around it. It's got a couple of interesting parts. There's a bright area on the top that people have labeled the knot. We don't know what it is. And there's a ridge on one edge that kind of looks like a circular line, and they call that the eastern limb. So we have a good sense of what the pulsar ring nebula does, but we really didn't know what was the stuff around it. Is this the edge of the supernova shell? That's the explosion that caused everything? Or perhaps is it a different type or extension of the pulsar ring nebula that's in the middle that we're now looking at and seeing for the first time? So when we took a look at this with NuSTAR, we did that. And it looks really blob-like. And you kind of wonder, well, how can you get anything out of that blob image? So what we did was very similar to the procedure that Hubble telescope did when they made a mistake on one of their lenses and they had to fix it later. But for a while they had this really bad lens. And they developed a method to correct for the blurriness that Hubble was putting on its images. And we were able to do exactly the same thing with NuSTAR. We were able to take away the blur or deconvolve the image into that. So now this is the first time anybody has ever seen any of these weird external pieces of light at energies above 10 keV. So you can see the 3 to 6, the 6 to 10, the 10 to 15, and what I'm not showing because the image is sort of hazy is the 15 to 20 keV picture. So this is really cool. We can see awesome structures. And using the emission, or the radiation that's coming out of these weird parts of this haze, we were able to say that the knot, the one that's at the very top, is the ejecta from the supernova hitting a clump of material that just happened to be there. And we were able to constrain certain properties of the eastern limb, although we still don't know exactly what it is. So NuSTAR has all kinds of capabilities. These are just 3 examples of some of the really interesting science that's being done now. I think in total we have 300 papers that have been published just from the launch of NuSTAR alone, and it doesn't count papers where NuSTAR adds information to, for example, a radio observation that's the primary point paper. So we have about 280 NuSTAR primary papers since the launch. That's incredibly productive. We're getting so much really interesting science from it. So if you want to come and talk to me about some of the other cool stuff that we've done, I'm happy to answer any questions. But that is it for my presentation.
Cool. So we have time for a few questions. If yeah.
Where is NuSTAR going to right now, or like how easy is it to maneuver it and serve as a step?
So it's really easy to maneuver NuSTAR. But because NuSTAR, we don't want to waste time, so every single second, NuSTAR is either pointing at something that has been predetermined to be important or moving to something else to look at. And so the schedule is planned, I think, several months in advance. So it's always full looking at something. I have no idea what's looking at that one.
When you were doing calibration, what kind of pressure do you have to calibrate PVC tubes?
So it's about 5 torr. PVC is a porous material, so you really can't suck all the air out because some air will come trickling through the plastic. But getting it to 5 torr was enough for the length that we have.
What's NuSTAR's expected lifetime and how's it doing on
NuSTAR is great. We have a solar panel that provides all the energy we need. So I think the limiting factor for NuSTAR is how much funding we get from NASA to keep it going. Because it takes people on the ground to make sure it's pointed correctly, to make sure it communicates with the satellites on Earth. So there's a lot of support that happens that needs to be paid for.
Okay. So let's thank Mel one more time. And thanks everyone for coming. If you have more questions, feel free to ask Mel or any of our volunteers in the red shirts. Thanks.